Yeah, 1 minute. So can you guys see the screen? Yes. Continue with? No, today is calculus. Today is the calculus. Yeah, that's right. Today is calculus day. Actually, so we are doing this calculus class or analysis classes, kind of a mixture and both. So after a long time, we missed the last week. Okay. So that's why this week I wanted to do it a little early. Okay. So last time we were looking at parametrizations and such. Last time we were looking at parametrizations. When is parametrization possible? Possibility. So I have not taken this from any book. So this is from a bunch of places. Okay, so some of it is from something called algebraic geometry, which is in little higher maths. And so, some of it, which I was going to say, comes from implicit function theorem, which is a theorem in multivariable analysis, but I tried to make it in a single variable case and say it. And some questions are just problems in parameterizing and finding solutions to that and so on. So yeah, I cannot for this particular thing, but for other things I will refer to, yeah, but to the books. But today we will not look at parametrizations, okay, to begin with. So let's not go into this because today I want to go back to the mean value theorem and the Lagrange mean value theorem and Rolle's mean value theorem and actually solve some problems using it and trying to see it through different angles, weaken some conditions and do those kind of things. Okay, so let's give a brief overview. Okay, let's give a brief overview of how we started from the mean value theorem, what was the purpose of us doing that theorem and how we came to parametrizations. But then we'll not go further in parametrizations today and actually solve some problem. So how did we start? So basically you see there are two things. What we were trying to do is we were trying to formalize and prove. Formalize and prove what? So we were trying to formalize and prove some geometrically evident facts. This is what analysis or calculus, well, not much so much calculus, but analysis is about, right? The proof part of calculus is about. The proofs are usually, I mean, the statements are usually geometrically obvious sometimes, okay? I mean, at least the kind of things we were doing. So we were trying to formalize and prove geometrically obvious or evident facts. Of what nature? What kind of facts? There are many. So what we were trying to prove it's or seeing was things like when you have a function and there are 2 points for which the output is same. So let's say this is a function f and there is f of 0 and f of 1, let's say, and it is 0 at both the points. Then there must be a place where the tangent is horizontal. There must be a place where the tangent is horizontal. Obviously, that's right. So this is what we proved, right? This is very simple. And we had a certain specific notion of tangents and we proved it. And then we looked at, okay, let us look at these chords, arbitrary chords. So you take an arbitrary chord, you consider its slope, and then it turns out that there is again a point where the tangent is equal to that, to the slope of the chord, which was the Lagrange mean value theorem, which is you take an arbitrary chord, take its slope, this is what it represents. Then there is a point, some point, we don't know what that point is, where this slope is attained. These were geometrically obvious facts related to existence of tangents, okay, parallel to arbitrary chords, parallel to slope of arbitrary chords. So this was the nature of our statements. It's very important to abstract out, though these are again easy, straightforward things, but abstract out what we did, because unless we do that, you will not be asking questions of how to generalize this in larger settings, like what if this was not the graph of a function? then how would you state the result? How would you formalize the result? How would you define what a tangent is in that case? And then how would you state your result? And then how would you prove it? Cauchy mean value theorem was an example of it. Okay, but so let's clearly state what we had. So these facts were of this nature, right? Existence, at least these two examples you can understand clearly, are of this nature. Existence of tangents, I should say, existence of tangents parallel to any, and that is very important, any arbitrary, or this is redundant, but I'm just trying to stress it, so mentioning both, any arbitrary chord. These are the natures of these results. One second. Right. And then we were trying to ask, how can you generalize it for other kinds of curves, right? The next question was, generalize these things for other kinds of curves. Generalize for other curves. And this is where it becomes tricky in a lot of ways on the level of formalization and stating and then proving. Proving is maybe easier, but the real challenge is formalizing what do you mean by what you say, what you see rather, and then how do you state it in terms of equations. And then proving is usually a consequence. Well, some, not always, of course, but yeah. And this was like, if we take some arbitrary curves, suppose this curve. Now this curve as a subset, it's very clear what it is. It's just a subset of, it's just a subset of R2, right? It is just a subset of R2. But if you just view it as a subset of R2, then how do you define what a tangent is for this curve, right? But then even for such curves, we feel, well, what does it mean by such curves? So yeah, we'll see. But yeah, we feel that if it's a roughly reasonably nice curve, then we feel that this tangent there should be, for a given chord, for a given chord, there should be a tangent that is parallel to that chord. Like we feel like that, okay, for good curves. Now, what is an example of good curves? Example of good curves is a curve, or let's say even if this curve is given, right? If you can write this curve as a function from, if you can write this curve as a function like this, and let's say, so this is a function which domain is R and is R square. And let's say the domain is not R, but you can always, usually you can do those things. Let's say something like this. If you can, and if you can show that the image of this function that is t2 ft comma gt, if you can show that the image of this function is this curve, then we saw that Cauchy mean value theorem answers that, okay? So then the incentive comes to look at curves which are defined as set theoretically or defined as using equation, and try to find a parametrization. Try to basically describe that curve dynamically as a function of time from t to ft comma gt. So points on the curve is ft comma gt. Not all curves can be written like that. So which curves can be written? And if they can be written, then what is the nature of f and g, right? And so on. How for locally or globally can they, and then if they can be written, then Cauchy mean value theorem says that for these kind of things also such things exist, but we will not go there. So that's why this is called parametrization of a curve, or just a subset of R2. You're parametrizing it, meaning that you're covering the points by, you're basically seeing this as a journey along time, and you're having some functions. Not, so it cannot always be done for all things, but so on and so on. So it's important to ask when it can be done and so on. But we will take a step back and in fact just look at these things today more deeply and solve some interesting questions and generalizations. Okay. So any questions so far? Okay. So let's remove this generalization here. So that's already an interesting topic, but we will not go there right now. Today, we want to take a closer look at the Lagrange mean value theorem. Obviously, this will keep coming up even in integration and so on. Look at Lagrange, or just say MVT. Can anybody say what Lagrange mean value theorem says, apart from the way I have already said what it means? Does anybody see it in a different way? Yeah. That is something that I've already said, in fact, already written. Existence. Can we see it? Does anybody see it in from a different perspective? Okay, like how does it help us to understand the function, maybe from that perspective? That is something more that is already there, evident in that is already written. I mean, what I will be saying will also be very evident, as it usually is, but something more organic, something which is not in this equation, something that you can say to someone who has not even done, let's say, in any case, something more organic, a different way. Like, what does it say about the relation of derivatives and functions? Maybe. Okay, I think it's a very vague question, right? So let us do a very simple problem, and then maybe we can get a sense of, when we see the usage of this theorem, then maybe we can say that okay, this is what this is. These are the kind of things that this theorem does. So from a problem solver perspective, it will be easier when you see those kind of problems. You would know, okay, I need to use mean value theorem here, or I don't need something like that. Let's do a very simple. This is like a silly question, okay? Some sense, simple problem. So f is a function. F is a function from, let's say, close to a comma b. So a comma b, 0 comma 1, anything you can take is here, and it is differentiable. It's differentiable on open a comma b, but all that doesn't matter. Such that f dash c is equal to 0. Okay? Then what can we say about f? Without using the theory of integration, because there, the way we use it, we assume a lot of things. In fact, we will open those things up when we do integration. So what can we say without using any kinds of integration and that concept? What can we say about f? No, not something very complicated. So, okay, I'm sorry. The question is wrong. Okay, sorry. What I meant to ask is f dash x is, sorry, f dash x is equal to 0 for all x. Sorry, so the question was wrong. Open a comma b is usually the correct thing, but doesn't matter. Sorry, did someone say something? Yes, right. So f is obviously a constant function. So this obviously implies that f is constant. How do we demonstrate? How do we prove it? I think someone is saying something, but you have to be louder. Okay, fix A. B is already here. So maybe you can take a C. Right. That's right. Yeah, you see. So this is again f dash sum D between A and B, where this is 0. And so FC equals to FA. Very simple. You see, this is very simple, but suppose you did not have the Lagrange mean value theorem. Try to prove it without that. Try proving this statement without the Lagrange mean value theorem. You see, you will have a tough time. So this is a challenge. Well, I can't really say, but because you may use the proof of it and so on, but try to just think, suppose you did not have this kind of statement, then how would you do? How without LMVT? Not now, just think about it because this is also a vague question. What does it mean by without using a theorem? But these kind of questions are usually, yeah, something like that. But we will soon ask this question very formally. We'll see. But you see, so what has the mean value theorem done here? It has basically helped us to see. It has basically helped us to see how the derivative controls the function. Yeah, it basically is basically like this, right? If some information is given about the derivative and you want to know something about the function, so it says these kind of theorems say that the derivatives control the function in a very strong way, right? So those are the kind of statements which you prove. So I think all of you know the L'Hopital's rule. So the way the L'Hopital's rule goes, right? Something like if this limit exists, f dashed by g dash, it implies that f by g limit also exists, right? But the converse is not true. So again, some kind of mean value theorem is used to prove the L'Hopital's rule also. That's another statement like that, which is obviously a bit more profound. Okay, so this is what the mean value theorem helps us to do, right? Knowing the derivative at all points, knowing its nature can help you to say about the function. And obviously there are many other results of this kind, increasing, decreasing, there are results of that kind. So obviously those things are there. Now let us ask this question in a slightly more general setting. So if you guys, those who are especially there, those who remember this, I think the way we came at Rolle's theorem was not by assuming that the function was differentiable. In fact, we proved a version of Rolle's theorem when the function is only continuous. That was the half chord kind of thing, right? That if you have this kind of situation, length 1 horizontal chord on the plane, then there will be a parallel chord of length half just for continuous functions. This is just for continuous functions of length half, exactly half. That is important. And then you can use this to show that there is a chord of length 1 by 4 and so on. And then you sort of get a kind of a Rolle's theorem without without differentiability. Then we kind of proved the Rolle's theorem, which was only for a function which has one-sided derivatives. Okay. So let's not go into that again. But right now we just want to focus on, otherwise keep digressing, this thing here. This result, okay, that we have here. What if f was not differentiable? Okay, so what if f is like this, and we just want to see, number one, how these kind of results can be generalized. Do they even physically make sense, and so on. Okay, and then we'll see how to prove them, and then we'll see that, well, proving them without having mean value theorems, because there you won't have mean value theorems, because you'll decrease the condition of you'll remove the condition of differentiability. You'll see how the proof becomes very difficult, or sufficiently more. If f is such a function and f is continuous, so continuity is something that we assume, otherwise the function can be too bizarre. F is continuous. And let's say that f is one-sided differentiable. So I'm just taking right differentiable for convenience. Right differentiable. Okay. So just 1 second. So we are trying to get to a similar result, but we are trying to just see, okay, how can we remove some conditions? Exactly. So can anybody define what is this? What is right differentiable at all points? How do you define this? So let me first not define it. Let me first just show you pictorially, because that's how you would have it. Suppose, okay, it's hard to draw it. It's because, but in the sense that it's going to be constant. But suppose you have from A to B, okay. And if you are noticing, and you have some sort of a function f, okay, and you don't have differentiability, but you have the following. Given any point C, when you approach from the right, given any point C, you're approaching from the right and you're seeing that the slope, that slope is existing. Okay, so I was going to say yes, but so what I was going to say is that suppose you have a function f. Suppose you have a function f. Forget about this. Suppose you have a function f which is continuous, and you are approaching from the right. And whenever, so given a point, fix a point and approach from the right. And whenever you are approaching from the right, you are seeing that the slope is 0, which means that, let's say that limit h 0 plus, you mean more h is positive, and yeah. So you are approaching from the right for any point. Rather make this x. And you are noticing that this limit is existing and it is 0. Let's say you have this. Let's say you don't have left differentiability. Okay, or let's say left differentiability is also there, but they are not equal. Now, this question is very important and interesting. It's interesting because we'll see the result still holds. And also it's important because there's a large class of functions which are not differentiable, but are very important. We will see some, I think we have talked about examples of such functions earlier, but we will also see it again, maybe in more details today. But here is the thing. Let's say you see this. So let's suppose this. Then geometrically, what does it, and this is what right differentiability means from the right. Then what should we claim? What would be your, instinctively, what should be the claim? And this is for all x. Obviously, I should mention that. For all x in a comma b. Let's say you just have this situation. Then what would you claim about f? Sorry. And leave it. Yeah, any guesses? While I'm doing this, just try to answer. What is happening? Shouldn't we still claim that f is a constant function? It seems like that f cannot really rise, isn't it? Right? F cannot rise. That's what it is, right? I mean, so the right differentiability, it just means that if you define your tangents to be, so you have a curve and you define you're extending a notion of tangent. So to see, the notion of tangent is very dependent on the context. There are hundreds of notions of tangents. I mean, there are many notions of tangents. I mean, not all of them obviously equally important or equally prevalent, but depending on the situation, we change our definition of tangents, right? We have already seen in the beginning of the differentiability classes. But right now, at least, well, I mean, sometimes you may just be taking the secants that are from the right, and you're taking the slope of these chords, and then you let these chords tend towards x from the right, and you're seeing, and that's suppose that's basically what this limit will be, those slope of those limits, slope of those chords tending towards x from the right, and you're seeing that all these are 0, means this limit is, the limit is 0, they are tending to 0, so the limit is 0. Then obviously, doesn't it mean that the function is not rising intuitively, right? So intuitively, the function is not rising. So basically, the claim should be that f is constant. Not turning is right. It's actually more correct. Yeah, not falling also, I should say. Not turning. Yeah, not changing, not rising or falling. That's right. Not rising, so symmetrically not falling. But yeah, should be both. Yeah. So the claim should be that f is constant, right? But how do we prove this? That's the thing, because now you see we don't have the mean value theorem because it's not given to be differentiable. So let's think about this. And the proof of this, we will learn some techniques, and we will also see that there's some techniques which we saw earlier for those who were there are again applicable here. Okay, and then you guys can think of a different proof obviously later on. But I will do this proof in the class because I think this is a interesting result. And So I will just remove this, and I'll just actually I should just remove this and say that f is right differentiable, and it's the right differentiables. The values of the right differentiation are all 0. Okay. So f dash plus, or I should maybe say this plus. This is basically a generalization of the notion of what is known as a partial derivative, or it can be seen in the same light. Okay, but yeah, so it's x is 0 for all x. Okay, so you know what that now we know what that means, and it is just the most obvious thing. How do we even get started with such a result? Let's just make this 0 comma 1. Okay, just to, because it doesn't really matter. Intuitively, yeah, so that's a intuitive reasoning, right? So that will help you to guide you to make this claim. How do we prove it? Proof is a very different thing, right? We have to establish it from the definitions that we have, and it is really needed because you see, if continuous functions can be very mysterious. Not, I mean, physical phenomena doesn't model all continuous functions, right? Velocity and so on. Not all continuous functions arise from velocity of some car or some particle, right? Continuous and things can be some very different than what happens in usual. So it may not even be correct, though in this case I'm just saying it is correct because I know it. But yeah, a priori you have to prove. Yes. Intuitively that's right. Instantaneous velocity from the right is 0, and basically what I also said. So that's correct. So again, this is also a geometrically or physically evident fact. How do we prove it? How do we get started? A plus and A minus, right? So you don't want to change the A to B, right? Why B minus? No, I mean the limit at a point. So you take a point and you take the left hand and right hand limits, and they should be same, right? Okay, so the endpoints are 0 and 1. So why should they be equal? No, but that's not clear, right? So okay, but then it's not clear that they are equal. I don't understand. Continuous means what? Continuous? No, but continuity is a very different thing, right? What are you saying? The limit here and the limit here are very different things. Or do you mean something here? Yeah, maybe, yeah, obviously. The derivative right hand limits are same, the 0. No, it's not like I don't want you to use. You cannot use. That is the whole, that's the You cannot use because it's not differentiable. It's not differentiable. Please be louder. What are the tools? That you can, any tools. So that's basically what I'm asking you guys. Now, how do you prove it? How do you get started? That's right. The converse is easy. Yes. The converse is easy. This is the thing. This would become trivial if f was differentiable, or if you had some sort of a mean value. So this is a motivation to try to generalize mean value theorems for right differentiable functions, if there is such, right? This is the interesting things. So you can ask from here. Generalizing mean value theorem for right, but that is seems like a very different question from this. Yeah, so that may not even be true. How do we prove this? Let's get started. I think, see, the way to get started with this seems like contradiction. Otherwise, how do you get started? You do have to take two values and you assume. No. So, no, but that's not exhaustive. Even its symmetric component doesn't make it exhaustive, because it may not be increasing, may not be decreasing. It may be something very complicated, right? So let's just assume that it is not constant, okay? Because we don't really have anything to leverage on. We don't really have anything else which we can use, right? So we have to. So it's essentially going to be non-constructive, right? So so this is just the start. Assume f is not constant, okay? I'll just write it mathematically. It just means that assume that there exist a and b such that fa is not equal to fb. And obviously we can just assume that a is less than b and fa is less than. These things we can assume because the other case is totally symmetric. I'm not assuming it's increasing. I'm just assuming there are 2 points like this. So there is a point A, point B. So this is your FA. And maybe FB is a bit bigger. Let's just use more space. If we have more space, some interesting reasoning have to be done from here. So I mean, there are a lot of results of this nature. We have even just for continuous functions, sometimes we ask questions like these. And then it becomes, you have to do some sort of epsilon delta arguments, right? Let's see. So this is FP. We want to say that if the function has increased from FA to FB, we would like to say, right, if the function has increased from FA to FB, meaning that the slope of the chord is non-zero, then there must be a place where the derivative has also risen, but we don't have access to the derivative. So how do we? So we have a certain line and we have a certain slope. It is the slope that, right, that is really the contradiction, right? That we have a non-zero slope is really where the contradiction should come from. Because the derivative is in terms of slopes, and so it's a non-zero slope, which is, we want to basically, we would like to show that the function cannot even rise. It can at no point rise. So here in this case, we just show that it cannot rise, not fall. right? Because we know that it has to rise, and so that's how we get the contradiction. So let's mark the slope. So we have this fb minus fa by b minus a. This is the slope that this is the slope which the derivative understands, or which the right derivative understands. That's in terms of which it understands function being non-constant. It doesn't understand this function is not constant or constant. This is what it understands. Okay. Let's just call this some, I don't know, some C, maybe capital C, change, or maybe just call it M. And so we want to show that the function cannot rise at all. That's what we have, at least intuitively. So how do we see? So the point is that, look, if the function has risen this much, right, then again, the continuity, right? So the function, I'm just drawing it, but the drawing is not obviously not a proof, and don't depend too much on it. Okay. Or if you depend, just see if your reasoning makes sense without the drawing also. Point is, if you have this, it's a continuous function, so it will be, so we're basically trying to use the intermediate value property here. See, if the function has risen from fa to fb, right, that much, then say there should be some intermediate point where it also rises by some non-zero quantity, right? So obviously this is not zero, or this is greater than zero, right? If this is greater than zero, then there must be a place where the function rises by something greater than zero, right? So what I'm trying to say is that there exists a chord, I should say an interior chord, and interior, because we have to use their interiorness, because just at the endpoints, what is happening, we cannot really use it too well. Okay. An interior, there exists an interior chord with slope something, some m1 that is greater than zero. Do you guys agree? In fact, we can even take m by 2, right? Because obviously, if the height is this, then there will be a place where the height is half, and so you can understand, right? The slope will be half of it. But you can take that or not take that. Depends on you. Okay. But my point is that there is a point, there is at least one point. So there is a point, maybe x naught, where the slope. So we are using this interior point because we can move when we are in the interior to do the reasoning. Okay. There is an interior point where the slope is m1. So I will just remove this thing. This was just the phrase. And we say that there exists x naught such that the main first thing that one must write is this, it's important, it's an interior point. And the second is that fx naught minus fa x naught minus a is equal to m1. Right? We know that such a thing will exist. Now, how do we take this reasoning forward? How do we create a contradiction? Yeah. So the idea is this. If this slope is m1, so if this slope is not that, but the tangent of that, if this slope is m1, right, then there should be a region around it where the slope is there should be a region around it where the slope should also be, at least m1, right? Something like that, or greater than m1. There should be a region where the slope is greater than m1. But then because the right derivative is 0, right, we can find a region in which the function rises by less than anything we want. So that is how we will sort of get a contradiction. Okay. Let me write it more formally. We know that there is a point where the slope is m1. Okay. Now this is what we will do. You look at all x. Okay. You look at all the x such that the slope is more than m1. You see that such things will also exist. Yeah, you agree again by the intermediate value property, because you have values above it which the function attains, and so the slope of chords will also be bigger than m1. So this set will be non-empty. Okay. Right. Okay. You take a look at all these points. So now I'll remove the phrase, write the thing. And this is the technique of constructing sets and taking their infimum, basically using the fact that we are in R, we are in a complete place. If you take a look, if you call this set, and so this set is all x for which is bigger than m1. Right, and x is less than b. Okay, we're looking at this set. Okay, where the slopes are all bigger than m1. So some point, 1 minute. Second, so yeah, so we look at all the points where the slopes are bigger than m1. So maybe this point slope is bigger than m1. It's hard to write, but you can understand. So these things will exist. Okay. Now what we do is we take the infimum of the set. So you see, the infimum means the greatest lower bound. Okay. So greatest lower bound. Roughly what this means is that, see, this is slope m, right? This red line is slope m because this x naught slope m. We are basically looking at all the points, could be less than x naught also, where the slope is more than. So you can see, right? You can see that the slopes are more. But then what we are trying to do is we are trying to take the least point in some sense, but it's not the least, because the least may not exist. So we have to take the greatest. So the least may not exist, but there will be lower bounds, and you take the greatest among them. Okay. And this technique is used many places, especially when you don't have good conditions and you want to prove a theorem. So the breakthrough theorems, which kind of take that jump, okay, into proving actually new things like uniform continuity and such, right? Of course, these can be replaced in terms using sequences also, that language also, but then maybe I have to say some word, Cauchy convergence and so on. So this is just saying it like this simply. So it's kind of, we're taking the first time the function, rises by a non-zero amount, that is m1, at least at more than m1. Okay, the first time that happens. Now you'll see a reason why I'm taking that. Okay. So obviously the infimum is now just a number let's call this number C, call it anything. Okay, so again, this is like the first time the slope becomes bigger than m1, but it's not the first time, it is the greatest lower bound. Okay, yeah, so it's like if you take 0, 1, the greatest lower bound is 0, which is not in the set. So, okay, it's the greatest lower bound. Obviously, I don't know, some of you may be comfortable with this notion, may not be. Knowing the definition is one thing, but getting comfortable with this notion is a different thing. So right now, we are not using it in very difficult way. So just knowing the definition, and I will point out the way we use it. Let's see. Let's try to see how we go from here. First of all, let us say that the infimum is C, right? So let us call this point C. I mean, for the time being, let us maybe forget about this for x naught. Otherwise, the diagram becomes complicated. Okay. I mean, in fact, you will see. Hold on, Ritham is here today. Oh, okay. Sorry, Ritham, there is no class today. Oh, I didn't mention that the class. Oh, no. Sorry. Yeah, there is no class today. This is a different. Sorry. Yeah. I didn't send a mail. Yeah, so usually on Wednesdays, I take another class. Yeah. Okay. So we take this greatest low. Okay. So the point is that what can we say? Let's think about this. What can we say about FC minus FA C minus A? What can we say about this slope? About the slope of this particular point C at the particular point C? You can just make a guess also. You see, the slope at this point actually cannot be bigger than M1. So actually the C will never be in the set, right? The C will never be in the set. The slope cannot be bigger than M1, right? Because see, if the slope was bigger than M1, if at C, if the slope was bigger than M1, so if this was bigger than M1, if, right, then you could find an epsilon, right? So once I can just try to do this. This is an exercise I'm going to do. This is also a continuous function, right? So you can find a small neighborhood, and you can go slightly to the left, and the slope will still be bigger than M1. Try to prove this. Okay, and again, it cannot be less than M1 also. Again, in the same way. Is it the same way? If the slope is less than M1, then just try to prove it. Okay, try to prove that the slope cannot be bigger. This is the exercise. Okay, the slope cannot be bigger than M1 or less than M1. It's going to be equal to M1. Okay, if you're comfortable with this, then you would already know this, that this should happen. Okay, but try to prove this, that the slope is M1 actually at that point. So earlier also we had located a point, but that was not useful. This is the least place where it happens, sort of. Okay, and that is what makes it important. I think so. Let's see. Yeah, that will feature in. Okay. So we have a point C where the slope is there. The slope is non-zero. But it's more than that. Okay. So we have a point C where the slope is non-zero, but it is the least place. It is the least such place where the slope is non-zero, where the slope is M1, you could say, maybe. or it is the infimum of this set, right? What does it mean? It means that it's a greatest lower bound, right? It means that if you take anything bigger than C, right? It means that if you take anything bigger than C, anything, yeah, it means that for any C1 bigger than C, no matter how close that is, if you take any C1 bigger than C, then you can find something here. So see, C1 is not a lower bound, right? C1 is not a lower bound to this set. And why must that happen? Why must that happen? C1 is not a lower bound to this set means that there is something less than C1 where the slope is bigger than M1. Is that right? Yeah. So if you take a C1, then you can find a D, you'll find a D where the slope is bigger than M1. It may be very slightly bigger, but there will be. Otherwise, C1 would have been a lower bound. And see, this happens for any C1. This happens for any C1. Now the problem is easy. You can so where should you use the definition? See this, where should you use the condition that the right derivative is 0? Should use it at the point C. If you use, so now you have to complete the problem. Okay, so use the definition at use simply use this, that this is 0. Okay, if you use this, then what do you get? Basically, you will get that there is a neighborhood. If you use this, you will see that there is a neighborhood, some C plus delta, okay, where the slope, okay, where the slope is less than epsilon. Now, for any epsilon, so I basically want to see the point is that the slope was m here, m1 here at C, and the slope has risen from m1 to some other thing, right? Will rise if you move to the right, if you move to any C1, the slope will rise. But 1 minute. So 1 second. Let's actually do this carefully. Okay, I think I'm making a mistake, meaning that I think we'll have to say something more. So if we, let's do it. Okay, so if we use this, then what do we get? We see that for any epsilon greater than 0, there exists a delta such that the slope, well, not just for that, but for all y, these slopes are going to be less than epsilon for all y in C comma C plus delta. Do you guys agree? This is the definition. Because the limit is 0, because the right tangent slope is 0, for any epsilon, no matter how small it is, you can find a delta. The delta will obviously depend on epsilon and so on. Right? So this is fine. One minute. So then if this slope is less than epsilon, one second now. Yeah, so basically the question here is what should you take as epsilon? So I think you should take it as M1 only. Okay. 1 minute. So yeah, let's do it carefully. 1 second. Yes, so it should be easy. Where do I write it? Yeah, let me remove these conditions. Yeah. Let me first say the idea, that way I'll also understand what to do. From here, what is the idea? The idea is that slope was m1. The slope was m1 here, right? And now if you just think about it, right? The slope was m1 at C. If you want the slope at D, for any D, if you want that slope to be bigger than m1, then this slope should also be bigger than m1. This little slope. Isn't that obvious, right? That slope should also be bigger than m1. If it's not, then you will not get there. That's an obvious thing, right? Okay, that's the thing. That slope has to be bigger than m1. So that's why we should take this to be m1 itself. So it's not coming out of the blue. Okay, if you just sit up with this, I'm sure you guys can do it, but I'll give you a problem which you will use similar techniques so you can have fun with that. This is also, I think, just trying to explore, because, but I'm just, obviously we're not discussing it really in some sense because that this one, but I'm just trying. Let's see. So for any m1 bigger than 0, we can manage this, right? And then you see, you can prove. Then you can prove that right? So then basically what do you get? You get that for any y, right? For any y, you get that 1 minute. Am I making? Yeah, I'm making a mistake here. There should be C here. Please point out the mistakes. Okay, I'm taking the C here, right? So this should be C, right? Now prove here from here that this implies is very simple, but just check. A lot of checks are there to be done. Please do them, because this is a theorem. This is a big theorem probably, right? It comes out like that. But the steps and the general techniques are important. Of course, knowing the theorem is also important, but this also, I think this is more important. Check that this implies that this will be less than m1. It's very easy to check. You can combine the thing. The real crux is that this is equal to m1 and this is greater than m1. Right? Sorry, this is less than m1. And again, you see, we use the lower bound, and now we will use the fact that it's the greatest lower bound, right? Now this is less than m1, so we have found a y where it is less than m1, right? No, rather, we have found a delta. So let's forget about the C1 now. The C1 was just, we were doing just to wishfully this thing. But now we have a delta. Let's just take this as a delta, right? Now, in all these, it's less than m1. But then we showed that we earlier showed, right? So this is the delta. The delta is bigger than C. Because the delta is bigger than C, it implies that there should be a D. There should be a D. There should be a D less than C plus delta, and in this, where the slope is more than m1. Is that right? Please write these things. Okay, this will be a good exercise to complete it. Okay, because that's the thing. So C is the greatest lower bound. Anything bigger, there is C plus delta. C plus delta is not a lower bound, and that's because there is something less than that, which is in the set, which means the slope is bigger. I guess that's a contradiction. Okay, yeah. So you see, the continuity was used very useful. It was used, okay, because basically you see when the slope is rising by this, we know that in between also the chord at least will rise by something. Okay, but then we had to go in the interior to do this, to really use the fact that this is 0, which means it cannot rise. But if you're at the endpoints, it's hard to use. Okay. So yeah, that is the idea. Now just check the details, complete the proof, fill in the details. I think this problem can also be approached in a different way. Okay, and that idea of that can be to look at the first point the function sort of rises. Instead of doing the infimum way, you could go the supremum way. Okay, so maybe you guys can try it. So you could consider this set, maybe you consider x such that fx equal to x fa, no, fy equal to fa for all y less than x. And then you take the supremum of this. Right. So when you take the supremum of this, it will be kind of be the first time it rises. Right. The first time it rises. And there you can do maybe a similar kind of argument. Think about it. Okay, this is something which you have to think about. So there's a lot of things to be done from here. So please do that. Yeah. So this is the major result, and we had to prove things. You can also use this construction of this idea in another problem, which I am just asking. Okay, let's not get into that. Let's ask some simpler questions now, and we'll get into that later. Let me just before we end, we have to just finish with. We wanted to do a few more questions, but we'll do one more. Yes, I want to do some examples of that, but yes, okay. Let us just look at another geometrically evident fact. Let's do, because this is think another geometrically evident fact. This may not necessarily need the mean value theorem, at least for the simple case, which is some sort of a exam type question. But then I have thought of a generalization of this, and I think that is correct. You guys should think about and try to prove it. But let me first take what the result is. You see, whenever you guys would have seen graphs of cubic functions, right? Just the ordinary cubic functions. I don't know if you observed this carefully, but if you see, they always are like this. I mean, in the sense that let's assume that the positive coefficient, the leading coefficient is positive, then you will see that they are always like this. I'm just focusing on this part. Just this part. You see, there is an asymmetry from the place of the, if you look at it from the place of the horizontal tangent. So when I just stated it geometrically, then I was thinking, let's think of some questions again. And this question I remember doing at some point, okay? But then there was a generalization today, which I was able to think of, and I think that may be correct. But let's think. The point here is that there is an asymmetry at the point where the horizontal tangent happens. You can take the point C. There is, so we all know that there will be a horizontal tangent, right? If you take three roots, so these are the three roots, three real roots, A1 less than A2 less than AC, let's say that three distinct real roots like that. So we can take this A1, A2, A3. Then we see that at the point where the tangent is horizontal, there is an asymmetry, right? So that's a geometrically evident fact. You guys would have seen it, right? So there is an asymmetry. This is spelling is wrong, it's double M. But in any case, asymmetry at C, or around about C. About x equal to C. Okay. How do you state this? So this is the thing. You see a geometrically evident fact. So this is a practice that we are doing, right? It's a practice of how analysis works in general, to some extent. Okay. Right. How do you state this? How do you this is the step of formalization, which is what we started with, right? You see evident fact, you formalize it. Here it's simple, very, very simple. And then you prove it. Even the proof is simple here. How do you formalize this asymmetry? Basically formalizing it and then reformalizing it and then further reformalizing it basically gives the proof. That's how proofs can be described computationally, right? But see, basically when we see this and what it is, we basically understand that we can say that C is closer to A1 than A2, right? Yeah. So f dash C is equal to 0. We know that this is a unique thing, C between A2 and A1. Then we basically want to say that, I'm just writing a slightly more, okay, that a C minus A1 is less than C minus A2. Prove this. How do we prove this? Let's think. So you guys should think about this. How do you prove this? Or before even you try to prove this, can you think of an intuition as to why this happens? Not evidence. The evidence is there. You see it in thousands of, you plot any number of graphs and you cubics, you will see it happen. That's evidence. But what is the physical intuition as to why this is happening? Because that will at least convince you that yeah, I understand the mathematical reason. And then the proving part is there, but the proof cannot be too hard. It's just a cubic. So by the way, this is a cubic. F is a cubic. F is a cubic, and A1 less than, strictly less than A3, 3 real roots. Can anybody think of a reason as to why? Not a proof. Proof you guys can try later on. It's not hard. It depends how well you can do it. That's really the challenge in this. How gracefully you can do the proof. But how do we explain the reason as to why this happens? Because this is important. A lot of times you should go back, you should have to go back and forth between the physical thing and then the statement and then the proof technique or the trick to be able to, you know, traverse these three things. Roughly what is happening is, see, the roughly what is happening is that you can say that this rises faster and this falls slowly. But why? Putting, sorry? No, it's just, no. It will just end. Yeah, we are over time. We'll just end in 2 minutes. 2 minutes. Yeah. Actually, I wanted to do a few more things, but yeah, I just went a little slow, I think. In any case, let's do. Yeah. So we're basically saying that here it rises faster, and here it falls slower. Why? How would you say explain it so that we can be sure that this will always happen? What is the intuition? Because that will be needed, because that's the intuition I use to make. Why? But why does it that for a cubic function? Because not for all, like for sine x, it doesn't happen, right? Symmetry is there. For quadratic function, there's a symmetry. But in cubics, there is always an asymmetry, and it's always of this type. That's a remarkable fact, right? It's obvious. We plot it and you can prove it also. I think you just write it, churn it out, you can prove it. But you cannot churn it out, I think, if it's an n degree polynomial, odd degree polynomial, at least you can say. So, well, I think the intuition should be that, see, the graph here, the function here rises and then it falls, right? This means that the derivative is a quadratic, right? The derivative was positive till C, and then after C, the derivative became negative, and then it becomes 0 and later on, so on. No, I mean the derivative becomes 0 here. So the derivative is becoming 0 here, but something else is happening. You see, the derivative. So I want to say that the function increases faster than it starts falling, then it falls. Okay. Why is it that? Why does that happen? See, it is because if you, okay, 1 minute, myself confused. Yes, can you think based on this model? Let's think this together. Think about the derivative. So the derivative climbs faster, then it takes more time to fall down. Yeah. So that is happening because you see the second derivative, right? The second derivative of this thing or the derivative of this thing is negative, right? The second derivative is negative, okay, which means that the derivative is negative. But the derivative of this is negative, which means that the second derivative of this is negative, right? But the derivative of this is increasing, right? It is negative, but it is going towards 0, right? So the second derivative is increasing. Sorry, the second derivative is increasing towards 0, right? And the second derivative is the rate of change of the change, right? And the more negative it is, the faster the change will happen, the faster that rate of change will change, right? But when it but when the second derivative goes closer to 0, then the derivative changes more slowly. And that is what happens here. The derivative changes very fast. Whatever it's increasing, decreasing is a different thing, right? But it's changing fast, right? But then the derivative changes more slowly later on because the second derivative is becoming lesser. The second derivative, right, is the rate of change of the change. And when that goes closer to 0, the derivative changes more slowly. And so it's obvious. You can write it, you will see it makes sense, right? That is really the reason. And you can use that reason basically in any polynomial. So try to prove this result and then generalize and try to prove this for any odd degree polynomial. It will be true. I think it will be true for any odd degree polynomial, at least. For even degree polynomial is also true, but you have to flip some signs and so on. But for odd degree polynomial is true. Try to state it and prove it. Okay, so that's the work you have to do. Okay, yeah. So that's it. That's it for today. Okay, thank you. I think someone else has joined. I think I made a mess today. I didn't mail for the other class. Unab, there is no class today. Sorry, I didn't send a mail. Yeah. No, sorry for my side. Yeah. Okay, so thanks. That's it for today. Yeah. Please try these things and